Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on chemistry for the upcoming JEE exam. And today is our 40th day. So we have started this chapter, that is organic compound containing oxygen, and we have completed one third, you can say, of the part of this chapter, that is aldehyde, ketone, and aldehyde, ketone, alcohol, phenol, and ether. Now we are remained only with this carboxylic acid. So the part of the JEE syllabus that is issued by NTA to be covered today is carboxylic acid and its acidic strength and factors affecting it. Plus, we will be seeing its preparation, properties, reaction, and etc. So let us start our today's lecture. So before that, let us see all the topics in a more detailed manner. The first one is preparation of carboxylic acid. So we will see various methods of preparation of carboxylic acid. Then we will see the physical properties of this carboxylic acid. Then we will see the reaction that will involve the cleavage of CO bond. So means this bond that is between C and O that is to be cleaved. In next we will see the reaction that involves COOH group. In the fifth number, substitution reaction in the hydrocarbon part, means suppose it's the carboxylic acid. So this one is the hydrocarbon part. So reactions including that also we will see. At last we will see about the acidity of carboxylic acid. So let us start our today's lecture. So we have seen this weightage earlier also. So average of one question comes from this chapter, which is of 4 marks. Before starting our chapter, this nomenclature, IUPAC nomenclature, you must have read this thing earlier also. But for carboxylic acid, this common name is also very important. Means it is important for various functional group also. But for the case of carboxylic acid, it is much more important. So especially if I talk about then this oxalic acid, malonic, succinic, and glutaric acid, adipic acid. So these are the common names that will be used in the JEE exam also. So you should know this structure by this common name also. Plus, if you talk about the aromatic one, then we had this phthalic acid. So this is phthalic acid that we have. So these are some common names of the carboxylic acid that you should be aware of, and plus the structure also them should be in your mind always. So a question may be asked directly using the common name rather than their IUPAC name. So let us start our lecture with this. So we will start with this preparation of carboxylic acid. So basically we will be seeing what are the methods of preparation of carboxylic acid. The first one is from primary alcohol and aldehyde. So we have learned this topic earlier also, that we can oxidize a alcohol or an aldehyde, that is alcohol that should be primary, and if in case if it's a secondary, then we can have a harsh you can say acidic medium. So a primary alcohol and aldehyde can be converted into this carboxylic acid. So we have seen the reagents earlier that were CrO3. Okay, so CrO3 was the one, and also we have seen KMnO4 that could do the work. Then we have K2Cr2O7. So I am revising all of those because they are used again and again. Now we have another say reagent which is very important, that is called as Jones reagent. So Jones reagent is nothing but it is CrO3 in presence of acid. So CrO3 is also a strong reducing agent, but instead of using it directly, we used it in the presence of acidic medium. Also, we can use KMnO4 in alkaline medium to hydrolyze, or you can say oxidize this primary alcohol into this carboxylic acid. So these are the two methods in which alcohol and aldehydes are converted into our corresponding carboxylic acid. Now, if you come to the nitriles and amides, they can be also converted. So what we do is simply we do the hydrolysis. So if you do the hydrolysis of this and then heat it, then you will get a carboxylic acid. Now in this lecture you will be confronting with various derivatives of carboxylic acid. So one of those is here, which is called amide. So what is amide? So first of all, what is derivative of this carboxylic acid? So this is the structure of carboxylic acid. You know it very well. So what we do is we substitute this group, that is OH group, this Z group, with different substituents. Like if it is NH2, it is called amide. We will see later on various one. So the first one you have came across in amide, so you should be noting this one down. Further, if we have an amide also, then we can also do the hydrolysis in the presence of heat to get our acid. Also, if I have benzylic amide like this, which is a benzyamide, we can do the, or you can say apply the same process to get our benzoic acid plus ammonia gas. So if you are doing it using a amide, you can get the ammonia gas also, because this NH2 is released. Next, the another method that can be used. So I have discussed this method earlier also. So what we take is KMnO4 and KOH and heat, and what we do is the oxidation of this benzyl group, sorry, alkyl group that is attached to benzene. Now the unique thing about this method is that you can convert a chain of any length. So you can see very clearly this is a length or a chain of length 3 carbon, lengthening 3 carbons, and this is a chain of length that is having 1 carbon. But in both of these reactions, the product is same. The condition is same, the product is same. So we do not change the condition at all. Still we get the same product for different substrate. So this thing is unique about this KMnO4. Now we get this as a, you can say, potassium ion. So what do? Is we hydrolyze this thing to get H at place of K. At last we get our benzoic acid. So this is a very strong reducing agent that can cleavage the bond between C and C, because here CC bond is present, and instead it is also cleavaged. So you have seen this example earlier also. So if you have an aliphatic chain like this and you have a secondary alcohol and you use this same method, that is this one, then on hydrolysis you will get C double bond OH on this side carbon. So suppose this is CH3, this is also CH3, and this is H. So you will get your product as this, that is acetic acid. Okay, so this is a very, you can say, a harsh medium that can be used to convert, or you can say cleave the carbon-carbon bond. Then next we had this from acyl halide and anhydride. So there is another derivative of carboxylic acid which is called acyl chloride. So again, in this time we are using Z equal to Cl for this acyl halide, and anhydride, so Z is equals to OCH3, OCOCH3. So if you draw it literally, suppose this is the carboxylic acid. Now we have seen three derivatives. First is Z is equals to NH2, in which Z is been replaced by this one. Then it is called as amide, and it is just a derivative of carboxylic acid. Second, if we have this Cl, then it is called acyl chloride. So you have seen this thing in this Friedel-Crafts acylation also. And third, we can have this O, CO, R, then it will be, suppose it is R dash, and it will be called as anhydride, amide, acyl chloride, and anhydride, acetic. So if this is CH3, then it will be called acetic anhydride, if this both are CH3. So these are the three derivatives so far. Later on we can encounter another also. So what do is we take a acyl chloride or an anhydride, we simply take the water, or in the presence of acidic or basic medium, we can get our carboxylic acid, means it is simple hydrolysis. So we are seeing earlier also. So amide was something difficult to break because we need somewhat harsh condition. We cannot use simply water and just cleave this bond. But in case of this acetic anhydride, it is very much, you can say, feasible to conversion to this benzoic acid. You can just pour water on it and it will simply hydrolyze and give you benzoic acid. Now, unique thing about this method is that both of this carbon, so CH3 COOH is getting one ethanoic acid and C6H5 COOH is getting a benzoic acid. Now, if you consider the acyl chloride, it is somewhat stable, so it requires some medium, like it is requiring alkaline medium to get your carboxylate ion, which on further hydrolysis gives you carboxylic acid. So this is all about your preparation from acyl chloride and anhydride. Next, we can do it from ester. So this is the fourth derivative of this carboxylic acid. So we are replacing this OH with R, OR, sorry. So what we will get is COOR. So this also on hydrolysis gives you the carboxylic acid. Only you have to see the thing is that which medium you are using in each case. So earlier you were using acidic medium for amide, plus you were using heat. Then when you came to your anhydride, you were simply not using any medium, you were just pouring water. Then if you come to this say acyl chloride, then we were using this alkaline medium, and further on hydrolysis you get your H plus. For ester also we use this acidic medium, or you can use the base medium also. This is the basic medium or this is the acidic medium. But if you use the basic medium, the thing here to notice is that at last you have to do this hydrolysis, because this carboxylate ion will be present in the presence of iron. So you have to apply this H3O plus hydrolysis to give you required benzoic acid. Sorry, carboxylic acid. So this is from the ester preparation. Now next, the very famous Grignard reagent can also be used for the same preparation of carboxylic acid. So if you see here, it is nothing but a nucleophilic substitution of this carbon dioxide. So what we are taking is, we are taking this RMgX and we are taking this CO2. So if you consider the CO2 here, then this is the thing that is having a delta positive charge on it. Now this R will attack here, and pi bond will resonate to this oxygen, and oxygen again will be hydrolyzed to give you carboxylic acid. So see, this is the ion that we get, and on hydrolysis we get our carboxylic acid. So this was all about the preparation of carboxylic acid. Next, let us see some of the physical properties like our boiling point and solubility, and many more physical properties. So let us start with the boiling point. So this carboxylic acid has a greater boiling point as compared to any of the functional group. So you have seen very earlier comparison of all those functional group. I have not discussed about this carboxylic acid, but let me make it clear. So if you are having some functional group like aldehyde, ketone and other alcohol in different molecules, and all these molecules are of comparable masses, you can say molecular masses, and you have an carboxylic acid of the same molecular mass, or you can say comparable molecular mass, then you will get the highest boiling point for this carboxylic acid. And what is the reason for this? The reason is simply the hydrogen bonding that is present between two molecules, and not just one hydrogen bonding, two hydrogen bonding. So if you consider the case of this aldehyde, it does not have in hydrogen bonding. Such hydrogen bonding is not present in carboxylic acid or in ketone. They just have a dipole-dipole interaction. But it has a dipole-dipole interaction, plus it has a hydrogen bonding. And dipole-dipole interaction, why? Because some kind of dipole is induced here, or you can say it's present here. Now, the next thing is to notice is that they can exist as dimer in the vapor phase or in non-polar protic solvent. So if it is present in non-polar protic solvent or it is in vapor phase, then it can form a dimer like this. So this is example of dimer that we are having here. So one molecule is this. So if I represent two molecules, so this is the first molecule that we have, and this is the second molecule that we have. Now both this molecule form hydrogen bonding and dimerize. So this having two, so it is dimer. And it is in vapor state or aprotic solvent. So why it is not present in protic solvent? So I will make this point clear in the next point. So next point says that solubility in water decreases with an increase in carbon chain length. Okay, so of course this carboxylic acid is soluble in water. Why? Because of the extensive hydrogen bonding that we are having. So you can see very clearly that one molecule is attached, then further a second molecule is also attached with this hydrogen, and a third molecule is also attached with this hydrogen. So an overall oxygen. So overall three molecules of this carboxylic acid are just attached with one mole of this, or sorry, one molecule of this water. So you can say that they are forming hydrogen bonding very efficiently. Now this is the reason they do not form dimer in protic solvent, because due to the presence of this proton that is present here. Protic solvent means, so if you don't know what is protic solvent, so it is something which gives us proton, free proton, simply free proton. Now this free proton will interact with this carboxylic acid and will disrupt the formation of this dimer. Okay, so this should be kept in your mind that okay, this dimer is only formed in presence of a protic solvent. In presence of protic solvent, it rather combine with the protic solvent's hydrogen instead of combining with each other. Now next, so this was about the physical property, that is boiling point and solubility. Now we will see the reaction involving cleavage of COH bond. So we will see various reactions. At last we will see the acidity, that is cleavage of OH bond. So if you consider a carboxylic acid here, so what we are cleaving is we are cleaving this bond here. So this is the reaction that we have here. So we are taking 2 moles of this ethanoic acid in presence of acid, that is H plus or P2O5, and then we are heating it to get ethanoic anhydride. So if you consider the reaction mechanism, so this H plus goes here. Now it has a lone pair. This will simply attack this center, which is nucleophilic in nature. This pi bond will go here and it will resonate back and kick out this water molecule. Now this H plus, which is bonded to O, it is given back in the solution, because this reaction is acid catalyzed, means it is acid mole will be given back, and this will give the final product as acetic anhydride, that is given here. Now next we have this reaction with ammonia. So what do? Is we take carboxylic acid and ammonia and they will react to give you acetamide. Now if you see these reactions one by one, you are just seeing that it is the reverse of the reaction that were used for preparation. So earlier we were just hydrolyzing this product to get our carboxylic acid. So if you just hydrolyze this product, you will get your carboxylic acid. If you hydrolyze this amide, you will get your carboxylic acid. But in the reverse reaction, what we are doing is we are simply reacting with the substrate that is required to be added to this carboxylic acid. Now for amide, we need this ammonia molecule, so we simply react it with ammonia molecule. This lone pair attacks on this OH and it leaves, and you get your ammonium acetate. You heat this thing and this thing get dehydrated, giving you the amide. Similarly, if you have benzoic acid, you can have the same reaction. Now if you look at a different reaction like this, which is nothing but an SNI reaction, okay, so it is an SNI reaction. You have seen this reaction earlier also. So this was used for the preparation of, so if you have this, you can use it for the preparation of the alcohol and other things. So what we do is we react it with PCl5 or PCl3 or SOCl2. So all will give you the same main product, only the side product will be varying. So what will happen is that this lone pair attacks on this phosphorus, this 2 phosphorus or sulfur. Why? Because all of this have vacant d orbital. That means they are good Lewis acid that will accept electron from this carboxylic acid oxygen Now this oxygen gives a lone pair to this uh, phosphorus in PCl5 or PCl3 and to sulfur in case of thionine chloride. Then it will revert back and give you the Cl. This Cl will again act upon this carboxylic, this carbonyl center, and will kick out your required product. So SO2 HCl. Then we have H3PO3, POCl3, and HCl. So you have seen a similar reaction, not the exact one, but something like this. So it gave you Rx. Okay, so this is all about this reaction of this carboxylic acid, which involve the cleavage of this COH bond. So all of this reaction involve the cleavage of CH bond. In this case, this COH bond is cleaved, or this one, you can consider any one. In this case also, suppose this is the thing. So this is cleavage here to attach this NH2. Similarly, if you consider this reaction, you have this OH here. So this is cleaved and Cl is added to give you RCOCl. Now each of these can be reverted back in using hydrolysis in acidic or basic medium to give you back your carboxylic acid. Now next we will see some reactions that involve the cleavage of COOH bond. Okay, so it is involving the reaction between the COH group. So basically there are two types. First is reduction, second is decarboxylation. So let us move to reduction. So children often get confused that which reducing agent will act upon which one. So I have told you earlier also, but I have put a more efficient chart here which will explain much better about the reduction thing. So in the given example, I have this LiLH4 or B2H6. You can use any of this, then it will hydrolyze it simply to give you carboxylic acid. So this hydrolysis is important in everywhere for the preparation of carboxylic acid, because whenever you do this reaction, you get a O minus. Now this O minus is present of an ion, so it is to be neutralized using the acidic medium H plus. Now let us see a summary of all this reducing reagent. So suppose these are the various carbonyl compound and one imine also, means carbon double bond N, that are reduced here. So we have 5 reducing agent here. NaCnBH3, NaBH4, LiBH4, LiAlH4, and BH3. So this BH3 is much more unique, so I will tell you why. Now if you look at this compound that are to be reduced, this is in the order of decreasing fashion, means this is reduced very means you can say that this requires large amount of strong reducing agent. Now this amide is less, you can say, as compared to carboxylic acid. Then we have this ester, then ketone, aldehyde, and imine is the most vulnerable to this reducing thing. Now all this reducing agent easily reduce this imine. So imine are reduced easily by all of this. Next, if you have this aldehyde, then this NaCnBH3 and BH3 also. So this BH3 has a very unique property. So we will see what is it. So if you first we will summarize all this chart that is given here, then we will see why it is unique. So if you have aldehyde, then all these three here are used for the reduction of this. Then if you move to ketone, so ketone has the same tendency almost, although it is a, means you can say a much more it is somewhat stronger, it requires somewhat stronger reducing agent amount to get reduced as compared to aldehyde due to the presence of steric hindrance on both sides, but it is almost equal to aldehyde. Then ester cannot be reduced using this NaCnBH3. So this yellow line denotes that it is reduced slowly. This green color indicates that it can be reduced easily, and red light means it cannot be reduced using this reagent. So ester cannot be reduced using NaCnBH3. Then if you move to amide, then most of the reagent are removed. So NaCnBH3, NaBH4 and LiBH4. But this case, this amide can be easily reduced by this BH3. But if you compare it with this aldehyde, ketone and ester, they reduce slowly. And although this amide is much less nucleophilic in nature, but they are reduced by this BH3. And same goes for carboxylic acid. It is also reduced easily by this BH3, and LiLH4 is somewhat, you can say, it is reacting slowly, and all other reagents do not reduce this thing. Now, what is unique about this BH3 is that upon moving from left to right, we are seeing that okay, we are just decreasing the reducing tendency of this functional group, but still this BH3 is working well within this range upon starting and end, but not in the between. Now, what is the reason behind that? So it is the reason behind that lies in the mechanism of this BH3. So all of this four reducing agent are hydride donor. What are they? They are hydride donor. Means how do they reduce? Is that they release this H minus, and thus H minus attacks on this carbonyl center and reduce all of this functional group. But BH3 does not work in that way. So how does it work? Suppose we have this carboxylic acid or any other functional group, then BH3, what does it have? It is a hypovalent compound, which means it is, you can say, it is electron deficient. So something that is electron rich in nature will easily get reduced with BH3. How? This will resonate here, and this lone pair will be donated here. Now it will form a complex which will look like this. Okay. Now you can see very clearly that this is having a positive charge. Now this carbon, which was initially having just a delta positive charge, is now having a complete unit positive charge. Now this boron hydrate goes here, attacks here, and make it as alcohol derivative, you can say. Okay. So now upon hydrolysis, so each of this reducing agent gives you a final product upon hydrolysis. I have told you earlier also. So this is removed and we get our RCH2OH. Now this is the reason this aldehyde and ketone, which do not have any set regenerating structure, that can donate electron to this BH3 as compared to this carboxylic amide and imine. Now why is this imine so green in case of BH3? Because imine has nitrogen as the donating one, and all of these have oxygen. Now nitrogen is much more less electronegative than oxygen, so it will donate it electron easily as compared to all of this to this BH3 and will get reduced using BH3. So this was all about the reducing thing. Now let us see some miscellaneous reducing agent. So that is, we have this diol H, which I have told you earlier is nothing but diisobutyl aluminum hydride. It is just a hydride donor also only. So it will reduce this ester. Okay, so it will reduce this ester via alcohol. So first it will convert this thing into alcohol. Then we will add more equivalent of this diol H to get our this thing. Okay, so this is unique about this diol H. Sorry. So this diol H convert this ester into this aldehyde. So sorry for the confusion. Or you can do it via alcohol also. Okay, ester. Now this amide, so it can be also reduced to this you can say ketone and not to the alcohol. Sorry, amide to this ketone and not to the amine. So this is this thing is to be noticed here is that amide is reduced to this amine and not to the alcohol because it has a N attached to it. Similarly, this imine is reduced to amine and not to alcohol. So this is important. Now if you want to convert this amide to this ketone and not to this amine, so what we will do, it will take this LiLH4 at 0 degrees Celsius. So it will convert this amide to ketone or aldehyde and not to this amine. Now This carboxylic acid can also be converted into this ketone. How? So what we will do is we react it with thionyl chloride. So you have seen the reaction earlier. It will give you Cl. Now this is a very good leaving group. So if you take a simple RMGX also, or any hydride donor like LiAlH4, it will reduce or it will give its H here, and this Cl will leave and you will get your aldehyde, or if you use this RMGX you will get your ketone. So this is all about the reducing agent. Now we have important reaction here that is used often in the JEE exam, that is called as decarboxylation. So if you look at the reaction that takes place, so it takes place like this. Suppose you have your carboxylate ion like this. So what we will do, it will simply resonate back here. So we will get this thing first of all, then it will revert back, okay, and give out CO2. Okay, so it will give your CO2 back. So if you want, you can do this reaction. So it is very important one, and it is present in the, it is done in the presence of heat and NaOH. Now it is another form also. So if you have something like this, okay, then also it can be converted. So what will happen, it will do like this. So what we are having is we are having an alpha hydroxy group. So suppose we are having alpha hydroxy group like this, then we apply a base here, okay, and not heat it, or you can heat it also. Then what will happen, this H will be removed, it will go here, it will simply move here to give you a ketone. So this is also an important reaction for the aldehyde. So it is also an important reaction, or you can say an example of decarboxylation. So we can reduce this alpha hydroxy carboxylic acid into, say, aldehyde upon heating and using a base. Now let us see some substitution part in the hydrocarbon part. So earlier we were leaving this COOH sometimes or sometimes OH or sometimes O with a bond between C and O. Now we will work on this part, that is alkyl group. So we have an important reaction, so it is called HVZ reaction or Hell Volhard Zielinski reaction. So it is a name reaction, so it is a very important one. You can convert this carboxylic acid into this alpha halocarboxylic acid. Okay, so how you will do it? You will take this X2, that is your halogen, which is to be substituted, and this halogen can be only and only chlorine and bromine and not iodine and fluorine. So there cannot be iodine and fluorine. So what you will do is you will take this H2O, and in the presence of red phosphorus, first you will react it with X2 red phosphorus, and in the next step you will hydrolyze this to get your final product like this. So what it is? It is a alpha halocarboxylic acid because halogen group is present at alpha position. Now we can have ring substitution also. So this is nothing but electrophilic aromatic substitution of this carboxylic acid. Now if you talk about carboxylic acid, structure of benzoic acid, and if you compare it with the general structure of electron withdrawing group, then it do look like the one. So it is an electron withdrawing group because a double bond is present here. So this thing is present here. Now this pi bond will resonate back to this carboxylic acid and it will deactivate the ring. Okay. Now due to this reason, sorry, now due to this reason it is you can say deactivating and it is meta directing. So we get upon nitration a meta nitro and upon bromination a meta bromo benzoic acid. So this is all about the electrophilic aromatic substitution of this carboxylic acid. Now next, let us move to acidity of this carboxylic acid, which is an important part for this carboxylic acid. So generally this carboxylic acid are acidic in nature. Why? Because if we just you can say deprotonate this carboxylic acid and give H plus in the water, we do get a structure that is having resonance of this negative charge all over this carboxylate. And since these two resonance structure are equivalent, they are very stable. So you should remember this point that if two resonance structure are equivalent to each other, then that resonating structure or that if case of conjugate base or conjugate acid, that will be very stable. So since these two are equivalent, it will be very stable and the resonance hybrid will look like this. Now next, how I will identify that it is acidic in nature. So if you react it with metal, simply you will get your carboxylate or you can say sodium carboxylate ion. If you use NaOH, we'll also get this sodium carboxylate ion, but instead of liberating hydrogen gas, so since we are not using the metal directly, you will get water. And if you use this NaHCO3, you will get water plus this carbon dioxide. But the main product is same for all of this. Now next, one simple thing is to be noticed here is that if we introduce the electron withdrawing group to this carboxylic acid, then its acidity will be increased. Sorry, this you can say acidity will be increased because the negative charge is stabilized by this electron withdrawing group. So our negative charge is well enough, you can say well known, that it will not be stable. Why? Because everything moved toward charge neutrality. So if something is negative charge present on carboxylate ion, it must be neutralized. So it can be neutralized either by resonance, or you can apply or you can say attach an electron withdrawing group which will remove this electronic burden on this carboxylate ion. So electron withdrawing group stabilizes this carboxylate anion. Similarly, if you have an electron donating group, it will destabilize it. Why? Because the negative charge on the carboxylate ion will be more burdened. So if you take in terms of simpler things, so suppose you are rich, okay, and now someone is you can say poor. So if you want to have a good society or a decent society, then the money should be distributed further that there is perfect balance in the society. Means each of you have a comparable amount of money. But if you give more money to the richer one and less money to the poorer one, then the rich will get richer and the poorer will get more poorer, and there will be a sense of instability in the society. So you can think it in the similar way that if something has negative charge and you are giving a negative charge to it upon addition, like electron donating group, using electron donating group, it will be not a decent one, or you can say in terms of electronic thing, you are disturbing its neutrality. Similarly, electron withdrawing group is stabilizing the electron neutrality. Now keeping that concept in mind, I have given you here a, you can say, comparison of various functional group substituents that are added to this carboxylic acid. So you can have a look upon this. Where you can have a look upon this. You can just take a screenshot and look upon this. It's an important series. Now if you summarize all of this chart, or you can say series, we will find that this group are in the increasing order of acidity. So CF3 has the maximum electron withdrawing group tendency, then NO2, CN, fluorine, chlorine, bromine, iodine, and then phenyl. So this is a very important series. So if you have a same carboxylic acid and only the substituent are changed, then you can compare any of those using this order. Now let us see some questions here. So Monocarboxylic acid are functional isomer or what? So if you look at here, so this is the monocarboxylic acid. So it is asked, it is a functional isomer of what? So ether cannot be the case because ether has only one oxygen. Amines can also not be the case because it has nitrogen. Alcohol cannot be the case because it has one oxygen only. Ester can be a case. Okay, so ester is not always the case. So it is, if you look at the structure, suppose we take a carboxylic acid like this. You can convert it into ether. Funk means just breaking the CH3 bond. So if you have a CH3O, CH3, so they both are functional isomer. Functional isomer. So this is the correct answer, ester. So the same thing is written here. Monocarboxylic acid and esters have the same general formula but different functional groups. So these are functional isomers. So example is C3H6O2 and C3CH3CH2OH or CH3COOCH3. Now this is a very interesting question. So I put some transformations here. So first what we will do, we will take an acetic acid and reduce it using LiLH4. So what you will get? So I have told you earlier, you will get your alcohol. So do not get hyped with this question. These questions are much more easier as compared to the one-liner question because you are given each step very clearly. Then further, this is A. Then we have this PCl5. So this is the reaction of the first chapter. So you will get CH3, CH2O, X here. That is Cl. Then what we will do, we will take this alcoholic KOH. Now what does alcoholic KOH does? It reduces, or you can say make it as double bond. So what do we call it? It is not acetaldehyde, of course, not acetyl chloride, ethylene or acetylene. So its name is ethylene. Okay, so this is ethylene. So this is the correct answer. Now again I have put another transformation here. So what I have taken? I have taken a toluene. So what does toluene look like? Toluene is this. Now upon addition of KMnO4, so I have told it earlier that whatever the chain length it have, it will convert it directly into this benzoic acid. Then we have this SOCl2. So we will give a SN type of reaction and you will get a acyl chloride. Okay. Then we have this H2PDBSO4. So you have seen this reaction. So if you want, you can guess it. It is nothing but your Rosenmund reaction. So sorry for this wrong spelling or wrong spell. So it will give you aldehyde. So it is a very good question. You can practice this question for your reaction improvement also, because encountering this type of question will keep you interact with all of the reactions with one question only. Okay, so if you compare this is the correct answer. That is C6H5CHO. Again, let us see another question. So the same thing is written here. So what is the correct sequence of reagent for the following conversion? So what we have to get is this thing to get this thing. Okay, so how we will do it? So in this place, you have to introduce one CH3 and you have to introduce two CH3 here also. So we are having some options, CH3MgBr. Okay, then we are having CH3MgBr, CH3OH. That is, it will give you esterification. So of course, it will not be the answer. Okay, then we have OH minus. So let us see the solution. So what we are doing is we are doing the tolerance reagent test. So we have seen this tolerance test yesterday also. So what does tolerance test does? It converts it into carboxylate ion. Okay, then we do the esterification here to get this thing. Okay, at last we provide an excess of CH3MgBr. So slowly each of this group is substituted and we get our final product. So this is the thing that we are having. So according to this, the correct answer is this one. Okay, so this was the fourth question. Now the last question that we have here is C8H6O4, it is heated, and upon NH3 what we will get. Now the options are salicylic acid. So let us observe each of the options one by one. So if we take salicylic acid, salicylic acid looks like this. So if we will heat it, then of course this will be removed. So it is a kind of decarboxylation reaction. Now upon NH3 it will not give any reaction. So this is not the case. So it is wrong. Now if you consider phthalic anhydride, for those who don't know, this is the phthalic acid. And if you combine both of this will give you phthalic anhydride. Now if you heat it, okay, so we are having, sorry for the confusion. Sorry for the confusion. Okay, so the compound X is, so I think this question is incomplete. Sorry for the confusion. So what we are taking a phthalic acid and then we are getting a phthalic anhydride. So this is the complete reaction that we are having. Okay, so sorry for the confusion. Now I will show you some questions. You have to do it by yourself. I will just show you one by one. You can take the screenshots. The first question. So let me give you a hint. So Clemmensen reduction of a ketone is carried out. So it is simple question. I put it from previous slide so that you can get a revision of all the concepts at once. Okay, next is when benzene sulfonic acid and p-nitrophenol are treated with NaCO3, the gas released respectively. So I have told you this reaction. So NaCO3 will give you CO2 of course. And for the p-nitrophenol, you can look it by yourself. Then next, phenol is treated with phthalic anhydride in the presence of conc H2SO4. The product is. Next, question number 9. So we have a alcohol, phenol. Okay, so phenol derivative. Then we treat it with HCl. So what will happen upon heating? And this is the last question that we have is sodium ethoxide has treated with ethynyl chloride. So the product is above reaction. So these questions are just a mix of all the previous concepts so that you can get a grasp of each of this. Today was the last lecture for the oxygen containing organic compound. So from tomorrow we will see the nitrogen containing organic compound. So thank you for today's time. If you want, you can ask any question. Thank you.